There you go. You're live. There you go, buddy.
Oh, there we go.
There we go.
Live on RIT set. Okay, sit down. Okay. Welcome to week 4 of RIT set. What do you mean 2 minutes early? We're live already. John told me I'm live. I can talk for 2 minutes until we wait.
Stay away.
What? Camera there. We got a new setup. Pretty cool. Is that the mic that's at? This is laptop mic, right? Boomers. Okay, well, I gotta talk for 1 minute until it's time to start according to Jason. So, hello stream. How's your day going? Mine's going kind of well. Woke up, had good breakfast. Hope you guys had good breakfast. Okay, almost noon. So Jason will be okay with me starting at noon. I don't see any messages, but I assume our chat is alive and buzzing, of course. How could it not be?
Fill it into a convertible.
Yeah, turn a fella into a convertible. The baby.
Turn a guy into a convertible.
Okay.
Alright, guys.
Yeah.
Gonna start.
Okay, guys. Let's go. It's noon. Welcome to week 4 of RIT Sec. Yeah, clap. Yeah. Remember to please sign in at signin@ritsec.club. Just know you're coming. You can. So sign in. You're here forever. Yeah, sign in so you know who's coming. And you get memberships. It's great. Go to the interest groups and programs. Pretty cool. Physical net, right?
Physical. Yeah,
Physical.
Showed up. Fuck you guys.
No one showed up for physical, sadly. Come on, if you want to pick lots, you're going to show up. Join our workplace if you haven't already. Lots of announcements on there. Cool stuff. Sign up for the newsletter. Get an email. Pretty nice. I remember the camera's up there now. ISTS is March 6th to 7th. Those are the team signups are probably already over. That's the white team signups. If you want to go help with the competition, do some nice work, help run it and stuff like that. White team's right there. Swag update. Again, lots of swag, sweatshirts, hats. If you ordered them, go to the club room. We'll help you get your swag.
What's up with that jacket, bro?
And we got jackets as well. So there's RIT Sec jackets. Looks kind of like this. A nice RIT jacket. Instead of the RIT logo though, you get RIT Sec. They're pretty nice. They're pretty warm. It's actually extremely warm. I want to take it off, but I'm modeling it. And the nice pockets as well. Honestly, I really like this jacket. This is the CCDC one. If you ever see the CCDC peeps wearing those nice jackets? Yeah, there's no way outline. There's a nice awful link, but if you go to Workplace, it's a much better link probably, so just look for the announcement in Workplace. RSec prize update, again, if you want to prize the RSec, go to the club room, they're there. And John has something about the blue team shirts.
John's turn to use his loud voice. Custom Ink has yet again canceled the blue team shirts because Custom Ink is such a great company. They are fantastic, customer service, awesome. So if you want a blue team shirt, please order it one more time. We have talked to them. Yes, we have talked to Custom Ink, and they will not be canceling the order again because we talked to them and told them if they cancel again, it's not going to be great for us and for them. So please order one more time. Thank you.
Okay. After that, we got B-Sides Rochester. Again, tickets are available. The cool virtual concert in Rochester. It's going to be online this time, but it's pretty cool. We got Emmanuel and John presenting. Pretty sick. Pretty cool. If you want to see them present, get some tickets. I'm sure Emmanuel has an amazing talk, like today. And movie nights. This Sunday at 7 in the conference room or on Discord. Probably going to be watching Inception. Pretty cool movie. You know, Mr. DiCaprio and stuff like that. Anyways, I'm going to be there. Pretty sick. Movie nights are fun. It's not the Lobster, sadly. And Weesis, they're doing a ice skating event on the 28th at 1. Yes, ice skating V2 with Weesis. So, check out probably Workplace for a more solid announcement. And we get a round of applause for our sponsors. Yeah, we love our sponsors. They're great. You love them? Yeah, we do love them. And yeah, follow social media on Instagram, Facebook, and Twitter.
Yo, do we have a MySpace?
No, sadly not. Without further ado, we got binary exploitation and reversing with our very own Emmanuel and Max. go.
Dude, you're gonna summon Stewart. Keep it down. Stewart is dead.
Sorry, just give me 1
He's
second.
not, bro. I saw him.
Oh.
No, I didn't know that. No, Stewart, you guys figment of your imagination. Stewart's just a figment of our universal. My crypto's my ass.
Okay. Here I'm back again with another presentation because Stuart doesn't even unavailable. Okay, binary exploitation and reversing. We some people know about this. We know the concept of it, but we'll talk about it again. We start with reversing. What is reversing? Well, it is pretty much trying to understand how things work, especially when that thing is closed source and you don't have full control over it. So trying to reverse it, trying to figure out how it works is the whole concept is the clear definition of reversing engineering, by the way. But in CSEC department, when we talk about reversing, or when I talk about reversing, the first thing most people think about is assembly, which is partially correct because there's other parts of reversing. For example, if you want to get the firmware out of a IoT device, sometimes you don't get the firmware binary. You have to extract it directly from the hardware. So that's a type of reversion. But in this case, that's not what we do. That's not what I do. So we are more of this. We have the binary, we have the executable, and we try to do stuff with that. So in reversing, there's not multiple ways. There's steps to doing reversing. The first step usually is static analysis. That's just pretty much getting as much metadata. Well, there's the basic static analysis, so you get the basic metadata, like when it was created, any possible strings, any if it's packed or not, and all that fun stuff. And advanced static is just reading assembly code. So if you really, really love assembly, then static analysis, advanced static analysis is for you. And if you're lucky, you just get to skip that step and go to just reading the pseudocode. And there's plenty of the compilers out there that can do that. Pretty sure people know about IDA Pro. There's Cotter, multiple decompilers out there. The ability to read the assembly code is just called disassembler, but we'll get to that point later. And you can also use static analysis to read obfuscated code. Oh yeah, binary ninja and all that fun stuff. Like I was saying, you can also use static analysis to read source code. Like if you remember from our previous presentation by Matt, the malicious JavaScript. If it's so, you can use static analysis just to kind of get the whole idea of how that works. But that's just static analysis. So back to dynamic, that's just running the program and figuring out what happens when you do. And just like the static analysis, there's the basic and there's the advanced. A basic is just running this, just running the executable and just seeing what happens. Does it create a file? Does it connect to a web server? All that fun stuff. And you just pretty much run it as it's supposed to and just see what happens. That's basic dynamic. Advanced dynamic is you kind of had like a debugger to that process or to that binary and see what exactly happens. And in that step, you kind of see the assembly too, but you're just doing like a breakpoint on different like areas of the binary you want to see. And it's most likely going to do this in a VM or a sandbox. I think most people are now moving to sandboxes now because if you don't have the infrastructure on your laptop or home, there's always lots of sandboxes out there, and you can just test your malware, and they can give you like a whole report about everything. So that's pretty cool. And so how and why do we do this? Well, next slide. We do reversing. Well, most people do reversing for fun. That's it's fun to figure out how things work. You don't have to do anything after that, but you mostly hear about reversing in malware
analysis, because for the most part we don't get the source codes for those malware. So in order to stop this malware, we need to reverse it to kind of see how it works. If it connects to a web server, so we can block every traffic to that web server. If it creates a file, we can keep a list of those files and know, hey, if anyone else has this file on your computer, well, you've been attacked by this malware. So it's used for malware analysis. And like I was saying before, it's also used to do some to explore closed source software. So let's say RIT has this fancy looking software and they want to do some bug bounty on it, and they said, oh, I'm not going to give you the source code, so just go. So you kind of have to reverse that step to figure out to do stuff. So there's like web app reversing where you kind of just reverse the API to get all that fun stuff. That's different stuff. But you have to be careful with that, because if you don't read their terms of service or whatever restrictions they have for you, it can be bad for you in the future. So be careful with that. Uh, you can also do it just to improve the software. I recently saw like someone reverse the GTA 3 video game, and they actually fixed a lot of bugs. They created a lot of plugins and all this cool stuff that the Rockstar's developers were not going to do. So it's also used to create to improve the software in general if you want to. Okay, time to get a little bit technical with the terms. I keep saying binaries, so I'm gonna switch between binaries and executable. I believe they're the same. I don't know if they are, but to me they sound the same because you execute something. So, and usually that something is a compiled program. So what you running, and that program can do whatever. It can be a game. It can be an application on your phone. Just anything that's compiled for the hardware to read or run. That's the binary. Then there's assembly, which is the human readable machine code. This is, I believe, I actually I wouldn't say I believe, but I think this is the lowest. I might be wrong. Lowest language we can read. I think below that is the binary code, the ones and zeros. So assembly is the one where we can actually read the source code to figure out what's going on, and it's usually a one-to-one translation. So as you can see, the 89D8 pretty much that's the machine code for the machine to translate to. But in assembly, it pretty much says move the registry ABX into EAX. If you don't know that, it's fine. You don't assembly is fun, but it's whatever. And after that is the machine code. So that's what the CPU understands. That's the ones and zeros. And that part we don't really touch that, except I except if you're doing some hardware reversing. I think at one point you might have to understand some machine code, but I might be wrong again on that. But some more terminologies. There's a, like I was telling before, there's this assembler, which is translating the binary to a readable form. So which is the assembly, which is what reverse engineers would most likely read all the time. And the compiler kind of like it reverses the compilation process. So rather than doing from the source code to binary, it's more like the binary to the source code. The source code is not going to be the exact code. It's just going to be a pseudo of what it might be. So most times they're not always correct, but they do what they have to do. And it's mostly seen in Android applications because there's a lot of decompilers out there for that, and it's free. So most people do a lot of Android decompiling shenanigans. And the debugger, I think everyone at one point have definitely used a debugger, especially in CS1 or CS2, where you have to debug your program to see what's going on. It's pretty easy, just interacts with the process, kind of just attached to that process, and keeps track of registries, memory addresses, and multiple stuff. And you can also look at set breakpoints at specific points if you want to figure out exactly what's going on or like what variable is stored at a particular point, you can always set a breakpoint. And yeah, let's see what's next. So okay, like I was saying, where does the assembly code comes from? Like I was saying, the assembly is like the lowest that we can actually read as human. That's that. But if we go higher, every time you do like a GCC, um, GCC and the input name, so the file, the C file, it gets compiled to machine code. But you, the short answer is by compiling C code, you can get the assembly. And I just want to note, you can also write assembly by its own. So if you want to do some x86 programming, you can also write x86 by yourself. You don't have to always go from C to assembly. You can also just write that by itself. So we're gonna do a quick rundown of assembly. Let's see how fast I can do this. Number one, it's a low-level language, and it's just programming extra steps. So you have to do everything yourself. If you're doing memory, make sure you can take care of that. John, he's gone, but make sure you know what you're doing, because you pretty much have control of what goes on. So if you mess up, you mess up, and depending on what you're working on, it could be bad. There's different type of assembly, which is based on different architectures. So there's the x86. That's Intel, right? Someone?
Yeah.
Yes. x86 is Intel, and that's what we see that mostly around. It's in the whatever this is, computers. Sorry, I forgot.
Well, technically x86, 64 is what's kind of.
I was gonna get there, but yeah, there's x86 is pretty much everywhere, and there's the 64 bits version of that, which is the x86 underscore 64. And there's a harm M1 chip coming up. You're gonna get used to that eventually. There's a Power PC that is previous, like it might still being used, but it's no longer like, I don't know. The Power PC is like a combination of, it was a collaboration between Microsoft, Apple, and someone else. I might be wrong on Microsoft, but three companies came together to create Power PC. And there's the MIPS. I don't know that. It looks pretty interesting. And today we'll just talk about x86 because that's much fun. So the way it works is it's instructions, just like how you do like x equals 5, how you create variables and all that stuff. There's the equivalent. But instead, we have like keywords. I don't know how many instructions, but if you click on the more, there's multiple. But the common one we know is move. So you move a value into a registry. I'll get to what registry is next. But if you want to assign, let's say, x to 5, it's going to be like move x, comma 5. And there's the had, which you just, again, you had numbers together. So subscribe, not subscribe. Subscribe and like this video if you want more reversing tips.
Hit that notification bell.
There's a lot of, again, there's multiple instructions. You can always click on that and read more about them. And that's the registries. So these are like the short-term variables. And there is 7 general use registries. So it goes from EAX, EBX, ECX, so on. And there's some special registries like EBX, EIP, ESP. I'll get to what those are later on. And there's the memory, the RAM. We all know what RAM is, and that's for longer term storage. Okay, registries. Like I was saying, there is a few, not a yeah, a few of them, and the general purpose one are like AX8, RAX, EBX, RCX, all that fun stuff right there, and they used to move data back and forth on demand. They're really fast, but again, they're not so many, so sometimes you have to swap the registries, so you can sometimes, like for example, move EAX 5, so you're moving 5 into EAX, and you can do move move EBX, comma 5, and then you can now do the add EAX. Huh. I remember, but you can do a lot with registries. But the few important ones are like the RIP, so instruction pointers. That just tells the CPU what command, what's the next step. So it's kind of like but I'm kind of going ahead of myself, but there's the stack, which is for every program, and the EIP points to the next instruction on the stack. Uh, yeah, like I said, it keeps track of the next instruction to be executed, like pointers. I don't know, it's funny. So more stuff. With assembly, you can access really, like I said before, you have kind of full control, so you can access like little bits of a registry, and we can look at, and depending on what architecture you have, there's the x86. In this case, this picture is an x86 registry, so that's going to be 32 bits. So the EAX should be the 32, and if you're doing 64, that would be RAX. So anything with R is going to be 64, and E would be 32 bits. Okay, and as you go smaller, so if you do 32 to 16, that would be AX, and if you cut it back in half again, it would be AH, which would be the first bytes, and the AL would be the second bytes of that registry. You can really do a lot with this. I think I have an example at the end of this. At the end of this. Whew. Wow, that's a really dark color. Okay. Yeah. Memory is just used to store information temporarily. It's hard, and if you don't.
They're doing stuff inside
Oh wait. Okay. In that case, I just quickly check something. Ah. Okay. I get there. Okay, memory is a pretty hard thing to do. I know some people who likes to do some low stuff would have come in contact with that and know how not fun it is to deal with memory. And that's why Java has some IO level languages. I have some fancy memory cleanup, whatever, so we don't have to deal with that. Oh, okay. And if you know how to do that, binary exploitation would be so easy. And yeah, it would be so easy for you to exploit. And memory is a heap of fun. So there's two type of memory. There's the memory that you have when you have your when you run your program, you're given a like a little stack of memory. But if you need like extra memory for things you don't know, you can always just use the hip to get more memory. So, and if you're good at this, well, you get a lot of stacks of cash. I read this morning, so I don't know if it's that good. Okay, stack. But it says stack of things, but it's just stack, which is for every execution you have a stack. Um, and a stack keeps track of multiple things. It uh, keeps track of the return value of when you call a function. It saves your local variables and function parameters. I don't think I have a diagram for this, but the stack is a really important data structure in assembly. And it grows from the higher memory address to the lower addresses. I'm doing from up to down, but like some people do from down up. So it's really it's up to you and how you want to describe what the stack looks like. And the way local variables work with stack is that it's gonna like start locating them from either the base pointer or the stack pointer. So a positive, you can get a, if you have like a RBP plus an X amount of offset. Now RBP plus an offset of let's say 80, and that would point to let's say the X variable. And just again to go back, when you have like in your Python program X equals this, the X does not really matter because it's not saved. X is not a variable in assembly, so that just it's just there for us to understand. But in memory, in assembly, it's more like saying move RAX equals 5. No, RA move EAX, comma 5. So just keep that in mind. And also stack is really important because it helps us create recursive function. So that the way that works is you have your stack, and when you call a function, it creates a stack for that function. So as much function you call inside of function, it's just a lot of stacks inside of stacks. And when it does that, it has to keep track of the RBP and make sure that, oh, when this function is done, I have to jump back to this RBP, the base pointer, and it goes on and goes on. Okay, and there's this. This is the free flowing memory just out there. We don't have, when the compiler does not give us, well, doesn't take care of this part of the memory for us. So if you need, let's say you want to get some extra memory for a struct in C, well, you have to use malloc. You have to tell it how much memory size you want, and it's going to give you that. And at the end of that, you have to free that memory. If you don't, you're going to have memory leaks. And yeah, so always check for those memory leaks because they are not fun. Because you don't want to see your what's a good program? You don't want to see your Safari using like all, huh?
Google Chrome.
Yeah, you don't want to see Google Chrome using all your memory. Yeah, did you see that?
Ah. Hey. Someone fixed it for me after
Okay, so this is how the stack looks like visually. The heap is usually the opposite of the stack because the stack grows downwards. In this case, it goes downwards and heap upwards. And when you create like variables, you get inserted into like in the stack, all that stuff. And if you do want to get that, let's say you want to get a variable in this part, it's going to be like the RBP plus whatever offset from that, and that would get you to that point in the stack. Okay, so we're gonna quickly go through some common programming constructs, so like the if statement, while loop, and all that stuff, and see how that is represented in assembly. So, like I said, all code has to run on CPU, so it has to essentially be written in assembly. So we'll show that. So including like if statements. If statements are pretty much just jump statements in assembly. So that's the jump instruction, which says if this doesn't work, you want to jump to this part of memory. So that's what the jump is. And a loop is pretty much the same, but instead of going forward, you're just going back, and that goes on and goes on until you break out of the loop. And you can also jump to different parts of the program by messing with the RIP. Remember, the RIP tells the CPU where next to go. So if you have a binary that's vulnerable to, let's say, buffer overflow, you can modify the stack to affect the RIP to point to some shellcode that you have somewhere. So if you know how to properly do this, you can do a lot of stuff with RIP. Oh. Okay, example. This is an if statement. Just checks if x equals 3. And on the left, you can see the source code, and on the right, this is the assembly version. Right here, you can see it is setting this part of the stack. So, like I said, it does like the RBP and the offset. So it assigns that to 1. And right here, it compares what's in that offset. So in that case, 1, it compares that to 3. So it's saying if 1 equals 3, so the jump and E, that's jump not equals to 0. I don't remember. Can someone double check on that? Is it jump not equals to 0? Okay, jump not. Okay. So if it's true, it goes to the left because this if check function. Oh no. It checks this if check false stuff, and if it's true, wait, I'm sorry. Okay, what it does is it checks, and if it's equal to 0, it goes to the right here. If it's not, it goes here. And this, I might be saying that wrong, but essentially this is how an if statement would look like. It's going to have the blue, not blue, the green and the red arrow, and that helps us tell where it goes. The green is if it's good, it goes there. If it's red, it goes the other way. And all, not, well, most of the disassemblers I've seen will have this kind of design to it. It has the part where it has to compare it, where it's comparing the variables, and it has two other branches that tells it where to go if one is true or not. Nah, no one get? Okay. And at the end, it just goes to the last block because it doesn't matter if you don't want it, just goes back here. And this is what a for loop looks like. An easy way to spot this, if you see this, just if you see this, just goes back and forth. That's an easy way to tell there's a for loop. Pretty easy to just look at, well, pretty much to detect if you're looking at some source code. Yeah, in that case, this is the old basic of a little quick snip of reversing. But now when you get the reversing, you have to have an intent to it. In our case, we want to do some binary exploitation. So reversing the binary and now trying to exploit that binary. And that's when binary exploitation comes in, and that will be taken by my partner right here.
Okay, so we've talked about the reversing, which is the low level stuff. That's where we're actually like in search. We're searching for what's vulnerable, and we can get a better understanding of that. Binary exploitation is abusing those flaws in software. Traditionally, it's something unintentional, or at least you'd hope it'd be unintentional. We're hoping that programmers aren't out there making purposeful bugs. So again, how to find these flaws or vulnerabilities. It's again just something unintended, and that those bugs are contained within the class of vulnerabilities. So furthermore, into finding these vulnerabilities, most commonly they're located in messy logic. So this can be something like just like repeated if statements, stuff that is just like checking the same thing. It gives us an idea that whoever the programmer is maybe doesn't know exactly what they're doing, so it can give us a good idea of, hey, there might be a bug here, something we can exploit. Similarly in that vein, if you spot like a bug, more than likely there's going to be another bug. More likely that one programmer makes another. Once they make one, then once after they make none. And also a nice thing to look at is what's important. This could be stuff like firmware drivers, important executables, anything that keeps stuff safe. So we kind of talked about analyzing the code, just understanding what it does and what's its purpose. And then we're going to talk explicitly about vulnerabilities, what they are, what's best for them. So good starting points for these are stuff like integer overflows, underflows. That's like when you're taking, what's like the upper limit, like 32,000, no, whatever it is. You're taking the highest integer, you're adding one bit to it, you're going all the way to the bottom. Similarly, you can be going all the way from the bottom all the way to the top, just by changing one bit. Array out of bounds, you're writing more data than is allocated, so you're actually going to be writing to the heap. Buffer overflow, similar to array out of bounds, you're going to be writing out of bounds of what is actually allocated, and of course, there's plenty more. So we talked about this previously. Wherever there's been one bug, more than likely, or more likely than not, there's going to be another bug. Programmers are generally pretty consistent. If they made one bug, probably two. If they've never made any, which pretty much impossible, but if they are known for not making bugs, they're probably not going to make a bug. Also, find important code to exploit or binary exploit. Look into it. This could be, again, firmware drivers, stuff that has like a sandbox like Google Chrome. There's tons of interesting things with sandboxes that you can exploit. That's just completely unintended. And finally, that messy logic. Which one? Yeah, if there's a bunch of if statements that mean the exact same thing, programmer probably doesn't know what he's talking about or doesn't know what he's doing, and he just got a workable version and sent it out. So mainly that's what we're looking for when we're looking at binary exploitation. So analyzing the code, we go back to the idea of reversing. Hopefully this code is open source. If you can take something and try to figure out what it does in C, it is so much easier than looking at assembly. Like this is, I forget what the program actually does, but yeah, it's beautiful. Manuel said it's beautiful, but that's probably like a few lines in C, and this is an entire infographic in assembly. So if you can ever get the actual source code, always much better than looking at the compiled assembly, because compiled assembly can take however many flavors of just hardware versions, stuff like that, and it has to incorporate all that, whereas source code most likely doesn't. Try it. We also have to figure out where we can actually make a difference. Like, so what? There's some potential vulnerability in some section that we can never access. We need to find somewhere that we have access to, and there's a vulnerability in order to execute binary exploitation. And yeah, these are generally just kind of overlooked when we're determining where to find an exploiting code. So there's two main approaches. First is the manual review. This is reading your source code, even reading assembly. It is long, it is monotonous, you're probably gonna fall asleep. It can be very hard unless you are very good at it. Similar, or on the other side, there's automatic review. So this is stuff like fuzzing. I think everyone, or if you've never taken it, CSEC 201, you make a fuzzer. That's basically just going through memory, seeing if there's anything that's exploitable for you. And it's kind of static analysis, it kind of isn't, but actually compiling code and using tacw all, that just gives you all the warnings, and you can figure out some stuff there. Again, very time consuming, unless you know what you're doing. So we're going back to those vulnerabilities and vulnerability classes. So they're mainly grouped into these. The buffer overflows also. Buffer overflows. We'll talk about this a lot more of this later. Integer overflows. Again, that's just manipulation of the bits. That just kind of runs out of memory, going from highest to lowest or lowest to highest based on if it's an underflow or overflow. If there's some memory of that some variable that is just completely uninitialized. So you declare it, you save the memory, and then you just never use it. Always a good place to look, and somewhere you can always save some stuff to go back to. And there's tons of just functions in C or whatever you use. There's always going to be those no-no functions like gets. It's always fgets you should be using, just because it's a lot more secure. Printf, if you're using %i, you can actually write to the actual buffer if you put in enough data, and plenty more. You can look up, there's entire wiki pages on these. So now we're going to actually move into exploitation. So buffer overflows. This is caused by allowing too much data in. So this is like you're saying, hey, I'm going to take in 16 bits, but I'm going to allow them to write 32. So those 32 are still going to get written. But the difference is they're not going to be written to the actual variable that you initialize or you declare. It's going to be written to data that, or to the stack in places where it wasn't expected to be. So example, I kind of went over this, but you have an array of 50 bytes, you read 100 bytes, now there's just 50 bytes of whatever you've written somewhere on the heap. And similarly before, stir copy, gets, these in C are very common for if you don't do them correctly, or gets really, you have no control. That's why they made it not, or not removed it, but made warnings about it. you need something to allow yourself a little bit more flexibility. And then main thing about all these with buffer overflows is you're overwriting something and using that new overwritten data for your own use. So we're moving back into the stack frames. Understanding this and how we overwrite data is going to be pretty much how we exploit, because this is the most. If you remember nothing, remember how the stack frame is constructed, because this is a huge. It's huge for anything binary exploitation. So we have our buffer, we have our gets, and that's our function. But in our main, we call it function. So when our stack forms, we create the main stack frame, and once it calls that function, it adds to the stack. So this once that function, that int function runs out, that's just going to become undeclared data space and will be overridden eventually. So our main one is to get something that's going to be up, further up, so that we can execute it. So one thing is like that return address. If we're able to overwrite local variables, get all the way into that return address, we can actually return to a different function that wasn't intended. So exploiting buffer overflows, we need to know what we can overwrite. Local variables, return addresses. We're really looking at those return addresses a lot, unless you're just looking to destroy some stuff. Like, just change. Or really, if you're not messing with the return addresses, it's a lot of just overwriting variables and just messing with the program. So if we overwrite the return address to the function, and say we overwrite it with a pointer to where we can get a shell, well, we now have a shell that we can use. So, and it's kind of outdated, but you used to be able to just insert your own shellcode. There's been plenty of advances in compilation that have prevented this. Of course, you can turn them off now, but who really wants to? So going back to the stack frame, we now have our local variables, previous base pointer, and return address. So in order to get all the way to that return address, we just have to write data more than that 16 allocated. So another form is ROP, or return-oriented programming. So this is that overwriting of the return pointer. So in our simple method, we made use of just like one stack frame. In reality, there's going to be plenty more, and we're going to be able to overwrite plenty more return addresses. So ROP is that you're able to overwrite multiple return addresses at once, and ultimately just control the stack frame how we want it. And again, those return addresses are from previous stack frames. So mitigations. So there's address space layout randomization. So the main thing that we've been going off of to exploit these is we know how the stack frame is built. Of course, if you want to get fancy, like ASLR, you can randomize where everything is. So you have no idea where it's going. This ultimately comes down to a lot of just randomization attacks where you're just trying to do it as much as possible in the hopes of it being executed correctly once. It's kind of hard. It's annoying, but it is a preventative solution. So yeah, so these randomization offsets are in sections, are in like the static heap, sometimes even in the program themselves, just to make you just to mess with the memory a little bit, so there are no just definites in it. Next is DEP, data execution prevention. This is also called as non-executable. So if originally the stack, anything was executable. As long as you had a pointer, it could go to wherever you wanted. So now with non-executable, even though that you write a pointer to memory, it can be classified as a non-executable portion. So even though it's there, the compiler knows better and knows that you don't want to execute it, and therefore it will. Yeah, again, breaks shellcode. And another really good one is Stack Canary. So when we're overriding stuff, it's just kind of like a brute force. We're just putting as much data in and hoping to get something out. Stack Canaries add a randomization buffer between that and the return address and previous base pointer. Of course, if these are just like all like null bits, easy enough to get around, but majority of the time Stack Canaries are going to be completely randomized, but they're going to be, and then whenever the return address goes, it's going to make sure that that Stack Canary is still intact. So if you overwrite it and it's the same as it was previously, it's going to be and if it's different than when it was randomized, it is going to just crash the program and say, hey, there's something wrong here. We're not going to run this. And then just some general tools, GDB, or you want to talk more about these, or?
Yeah, sure. Yeah, so these are some tools you can use. Most of these are sometimes installed by default on a Linux system, and these are used by actual like developers, mostly not mostly, but like I know kernel developers use a lot of this. So DGB is just debugger on command line. OBG dump, well, that returns like the assembly looking like result of a binary. Strings is really important. Everyone, that should be the first step you do anytime you come across a binary, because that pretty much prints out every possible, well, not every, but every ASCII characters it could find in that binary. So sometimes it could be a variable name or it could be a function name, and in the CTF environment it could be the flag, depending on how the authors designed that binary to be. Ltrace and ptrace, the ltrace just shows you when you run a binary on Linux, it obviously has to call some different libraries to use a function. So the ltrace shows you, hey, at this point it calls this library to use this function. And ptrace you just attach to the program and let you control it, pretty much like a GDB way it works. And the strace is just shows you the system calls. Let's say you want to think of it as you want to attack a system. So you want to say every time this any program calls, let's say the exec syscall, you want to do some extra stuff before they call that. So the strace kind of shows you, hey, every time a program runs, it calls all of this function, and depending on how advanced you want to be, you can always attack each system calls to further exploit a target. And if something is confusing, you can always use the man page, just man and the command. And if that doesn't work, there's always the internet, which has a lot of resources. So that's that. And sometimes if you don't want to use some command line tools, there's GUI or things like for the compilers and disassemblers. There's four. IDA Pro, everyone who have taken 202 or 201 should have seen IDA before. Coder is for macOS. I think it's actually cross-platform, but behind the scenes it uses a framework called Radar, which is pretty cool. I think I'm giving a talk about that eventually. So DN Spy, I think I spelled that wrong, but that is for Windows, and it's a decompiler for Windows binary. So exe, DLL stuff, it's gonna show you like the pseudocode for that. And Ghidra, we know what that beautiful machine or software is, created by our loving NSA. You can use it. It's open source. Use it. Yeah, use it if you want to. Use it if you don't. That's up to you. And there's multiple resources. So there's videos, PDFs, tutorials, many things. There's a lot of resources out there for you to learn about reversing and all that fun stuff. And I think that is it for us. So that is our presentation about reversing and binary exploitation. Hopefully you learned something today. We tried. Thank you. Oh, I forgot. Any questions? Okay, before we go, I do have some reversing jokes. I'm proud of myself. So the first one is just nothing because it what it does is increments a RAX, and again it negates that, so it pretty much cancels itself out. So it does that twice, so that means nothing, literally nothing. And this part is just this is just a cool trick. If you want to change alphabet, like change a lowercase to uppercase, you can just change that little 8 bytes. Remember from the uh, registry stuff, you can always just change a specific byte to whatever, and this would change from a lowercase to uppercase. I thought that was pretty cool. So there's a whole website that does a lot of these jokes, and yeah, that's it now. I'm done.
No meme of the day, bro.
Well, it's not a presentation for me. Oh, do you? Okay. So for demos this week, we are for some of them you get the binary. Sometimes you get the source code. So I'm giving you both side, and sometimes and there's a VM for this week, but you don't have access to them. You just have to connect to them. So they're like web servers, and you have to netcat into those specific port, and you get a prompt, and you do whatever it asks you to do. So yeah, I think now I'm gonna give a demo of the first two challenges so I can get you guys started. So give me a few minutes to set up, and I will get back to you. Wait. That's why I said give me a moment and I'll be back with the stuff. Okay, 1 second.
Dog. You are dog water. Dog water. No, this thing is dog water. POV, you are dog water. No, this thing is dog water.
Yeah, can you put it in? I'll be right back just to set up.